My name is Darby Mitchell. I'm a technical staff member at MIT Lincoln Laboratory and the principal investigator for the most recent phase of SPAR research. I'm going to describe how IARPA recognized both an important national need and a promising new technology that could address that need. We'll see how IARPA invested in that technology at a crucial moment in its development and sustained that investment across a decade, shepherding the technology from a proof of concept to a pilot demonstration in an operational context. MIT Lincoln Laboratory has been involved from the very beginning, leading the test and evaluation effort for IARPA and helping to shape the evolution of this emerging capability. Let's start by observing that the government needs to carefully share sensitive information across organizations and agencies. Let's take a look at a real use case that everyone can relate to. Here we have an airline with a list of travelers in the role of the data owner. We have the U.S. government with a list of persons of interest in the role of the querier. The goal is for the querier to obtain a list of persons of interest who are scheduled to travel on the airline. Let's assume that both of these organizations are reluctant to just hand over their information to the other party. There are very good reasons why an organization may be reluctant to share their information in such an uncontrolled way. Ideally, we'd have some sort of trusted third party. This would be an organization that both the querier and the data owner completely trusted with their data. The third party would take the list of travelers from the data owner and the list of persons of interest from the querier and return the persons of interest scheduled to travel to the querier. However, if these two organizations are reluctant to share their data with each other, why would they be any less reluctant to hand their data over to a third party? Even if you assume that you can trust the third party, you're consolidating all the sensitive data in one convenient location for an attacker. Instead, a better approach would be to develop a relational database alternative that provides additional privacy guarantees. The querier needs privacy for the query and the results. Otherwise, the data owner could just use their knowledge of the records in the database and the results to reconstruct the query. The data owner needs privacy for records unless they're requested. The data owner needs assurance that queries are sufficiently specific to discourage phishing expeditions. Recent advances in cryptography can satisfy these privacy guarantees and rebalance this trade-off between need to know and need to share. Now, you may be asking yourself, hasn't industry already solved this problem? The problem with the commercial alternatives is that we're really choosing just another trusted third party here. This time they're building software for us that we're supposed to trust. The technologies we're going to cover have been independently verified by Lincoln Laboratory. Their work has been published and peer-reviewed within the cryptographic research community. And our position is that the government shouldn't have to rely on marketing claims or service-level agreements for security. Now that we've framed the problem, let's look at what we're going to cover. Let's start with the typical architecture of a relational database. Here's the typical architecture pattern used by relational databases. The data owner operates a server that hosts the database. The querier can use a client to submit queries to the server and obtain results. We can see that this involves a single round trip between client and server, which is simple. However, the server has all the records, the server knows the details of the query, and the server learns which records satisfy the query. We need a better way to search that doesn't compromise privacy. Now let's take a look at the architecture of a privacy-preserving database. This is what the architecture of a privacy-preserving database looks like. We've added a third party called the owner, representing the data owner, and the server is now hosting encrypted indices and records. It's important to note that while the data owner provides plain text records and a policy specification when the system is initially configured, those are not needed at runtime. The assumptions we make are that the client could be malicious. In other words, they are not necessarily following the protocol. However, the owner and the server are considered honest but curious, meaning that they must follow the protocol, but they may attempt to learn additional information. Let's look at the key challenges that had to be overcome to develop this technology. Papers in 1995 and 1997 proposed a new cryptographic primitive called private information retrieval. We'll use the now familiar roles of querier and data owner to illustrate the feature this primitive provides. The data owner has an array of records, and the querier wants a specific record from the array. PIR schemes enable the querier to ask for and receive a particular record without the data owner learning which record was retrieved. This was a promising new contribution to the field. The next step in the progress towards searchable encryption was coming up with a way to do PIR using keywords. In 2000, the Song, Wagner, and Perrig paper provided the first real problem definition for searchable encryption. Subsequent papers in 2003 and 2006 provided the security definitions used today and gave the cryptographic research community the tools to reason about the security of proposed schemes. By this time, the cryptographic research community had a pretty good idea how to do exact-equality search based on a single keyword, but there were no proofs of concept. Then, in 2007, a system security researcher named Radu Sion published a paper saying that if what you cared about was the privacy of the query, you were better off to just transfer the entire database to the client and allow them to perform the search locally. This called into question the future of this promising area of research. That's when IARPA got involved. IARPA launched a program to demonstrate the feasibility of searchable encryption. Lincoln's role as test and evaluation lead would remain consistent across what would become a series of programs. Lincoln specified the rules of engagement and the plan for testing, evaluated the security of cryptographic protocol designs, developed test infrastructure, generated synthetic data and query corpora for testing, and designed and executed both automated testing to evaluate expected behavior and operator testing to evaluate user experience. With Lincoln as the test and evaluation lead, IARPA launched the APP program. The APP program was an experiment to evaluate the feasibility of exact-equality search based on a single keyword. Database sizes were modest, just 100,000 synthetic records, and teams knew the schema years ahead of time. This early incarnation of the technology included policy enforcement as a pre-processing step that was performed on the client before the query was submitted. The results of this effort were truly amazing. This chart shows the overhead of response times for the three performer systems, Blind, Seer, Espada, and Stealth, when compared to unprotected MySQL. We can see that the three performer systems are in the neighborhood of 1.3 to 1.6 times the overhead of the unprotected MySQL baseline. The chart also shows the overhead of MySQL with transport layer security enabled, compared to unprotected MySQL for reference. These exciting results led to a substantial expansion of searchable encryption research. The SPAR program focused on scalability, 100 million synthetic records, terabyte-scale databases, and flexibility in the diversity of query types. Range, subsequence, wildcard, XML, ranking, and stemming queries could now be combined with keywords using Boolean expressions to construct complex queries. Teams still knew the schema and characteristics of the data well in advance of testing. Metrics now included integrity of records returned and atomicity of query responses interleaved with updates. Policy enforcement was integrated into query processing, as the performer teams each designed and implemented their own policy enforcement mechanisms to express and enforce restrictions on what were considered valid queries. The results were again very encouraging. The chart shows that while each performer had challenges with certain query types, overall, these systems achieved less than 3 times the response time of the unprotected MySQL system on 7 out of 11 query types. The most amazing thing about the SPAR program was the diversity of the technical approaches developed. Each approach uses a different technique to construct secure indices for each column and query type, and each meets the minimum definition of security that Lincoln and IARPA specified. All 3 of these implementations participated in the next phase of research. The Director of National Intelligence asked IARPA to do a pilot demonstration of SPAR technology on an operational network with real data and real operators. The focus for this phase of testing was on usability and responsiveness. Metrics now included more qualitative measures such as user experience and policy expressivity. The policy enforcement mechanisms were evaluated against the rules the government wanted to enforce for this use case. One finding was that the performer-designed policy enforcement mechanisms were not sufficiently mature to support the government's needs, and additional investment was required. Another surprising revelation was that operators cared more about predictability of response time than raw performance. It was more important for an operator to be able to predict query response times so the tools could be more easily integrated into the performer's workflow. A quote from a SPAR pilot participant sums up the overall feedback. They said the technology was easy to use and would definitely be helpful to the community. Additional results from user experience surveys were that users found 2 out of 3 systems to have acceptable timing, and they wanted to use the technology. Now, it's important to fold the lessons learned in operator testing back into the technology and address any limitations identified from operator feedback. IARPA did exactly that with the SPARS program. The government selected just a single performer, Stealth, from the SPAR pilot to continue on the SPARS program. One goal for SPARS was on dynamism, or database changes over time, and its impact on query performance. Going back to the national need, flights get canceled, travelers change reservations. The system needs to accommodate that sort of dynamism with minimal impact on query performance. Additionally, Lincoln Laboratory specified both a query language based on a subset of SQL and a policy language to better address the government's needs and the previous performer-designed policy enforcement mechanisms. Measures included variability of response latency as well as update efficiency. We've talked about results from prior work, but what really matters are the most recent results that reflect the current state of the technology. Let's take a look at the test setup and then the results. Remember this diagram showing the architecture of a privacy-preserving database? Let's take a look at the test infrastructure we created for automated testing. Our test infrastructure in AWS GovCloud included the 3 components of the system under test, as well as a test management server and a MySQL database for ground truth. Let's look at the correctness result. We tested over 3,800 unique queries. The system returned correct records for all valid queries and correctly rejected malformed queries. Stealth's policy enforcement was consistent with the Lincoln-developed reference implementation 99.98% of the time. We analyzed the 3 inconsistencies and found that they had a common root cause, which was not a security issue. Now that we've verified the correctness of the system, let's look at its performance. The graph shows performance for queries from 1 to 50 terms in size for both MySQL and the final version of Stealth software. The vertical axis is query response time in seconds on a logarithmic scale. Overall, performance was good, with a quarter of queries returned in under 2 seconds. You may notice that the average latency for the Stealth system is more than 3 times the average latency for the MySQL system. That's because we've included some pretty big queries in the results. While searches on person-oriented data are typically not a large number of terms, for example, first name, last name, and date of birth, the sponsor had seen some very large queries in operational use and wanted to make sure the performer system could handle large queries. 75% of queries returned in under 7.5 seconds, but the larger queries were outliers that significantly skewed the mean. That's why the average for the SPAR system is more than 3 times the average for the MySQL baseline. For update efficiency, response times increased by 67% after updates were applied. We determined that if we added a periodic maintenance window for the performer system, we were able to run some maintenance scripts and eliminate the overhead associated with updates. This maintenance cycle had additional security benefits as well. Determining how often to perform maintenance would be a use case specific trade-off between optimizing query performance versus the immediacy with which updates were incorporated into query responses. We saw very modest overhead for policy enforcement, and it didn't vary much across policies. So to summarize, IARPA's timely investment and continued commitment help make practical privacy-preserving database search a reality. There are a diverse set of query types available. The system demonstrated reasonable performance overhead compared to an unprotected relational database, is secure against malicious clients, supports terabyte-scale databases, and offers robust policy enforcement. Lincoln Laboratory has validated the security, correctness, scalability, and usability of SPAR technology. The developers of the most mature system say their product will be commercialized this summer. Lincoln has described the future of the field in the first Systemization of Knowledge paper on searchable encryption at this year's IEEE Security and Privacy Conference. I'd like to take this opportunity to recognize the members of the SPARS team who contributed to the most recent phase of work. Over the years, many Lincoln staff have contributed to the evolution of privacy-preserving databases and searchable encryption. There are just too many to fit on one slide. I want to express my thanks to the SPARS team and the outstanding support we receive from our contracting office, security office, and the director's office for helping make this program a success. Since this program started, hundreds of papers have been written describing breakthrough work in this area, and we're excited to have played a small part enabling some of these breakthroughs. If you'd like additional information or you have questions, please feel free to contact us at the email address shown on the screen.